Yeah, welcome to this proper test run. Really great to have you for today's session of our industry briefing. As I have announced it before, this is really a test run. We want to try a new tool, so bear with us for any hiccups today during the call, but we hope you really enjoy it. I will also go a little bit into the details of what you need to know. Cool. That's so great to have you, Peter. Feel free also to message everyone in the chat as Peter has done. Really great to see you here. As I mentioned, today's session, we will try a new tool. Thanks a lot for Nick, for testing with us. This way, post-production will get way easier for us. And as you all know, we are a small team at First Momentum. I always call us a seed startup in itself. So this will allow us to automatically create transcripts of also these sessions, also snippets, and so everything that also helps us to make this experience better for you afterwards or for the ones that couldn't join. Plus, we plan to also bring more external guests onto these sessions. So other VCs, other startups. So this would be also the great tool to actually run public sessions. So some things that change kind of in a way. Chat is the same. You have the chat. Feel free to just message everyone. We can see that as well and also respond to you. Then later on after, but also throughout the session, if you have questions, you can either put them into the message chat and we will get back to them in the Q&A part, or later on also feel free then to call in. This is kind of the way that you can then also speak up. The tool will ask you to provide like a comment, what do you want to ask. If it's also a comment on something that someone else mentioned, please just mention this quickly. But we see that and can then just accept your call in. It really feels like television. So And for the networking session, which we usually start, quarter to one, or usually we do this in the evening. So today it's also the first time lunch and learn. But for the last quarter, I will share the Zoom link and whoever then is up to meet Nick, me, and some other folks also from First Momentum, just switch over to Zoom and we will do some breakout rooms. But happy to switch then over also to Nick. Nick is actually originally from Munich, but currently back in London. He did his summer internship, MBA summer internship with us, First Momentum here in Munich. Now back in London to finish his MBA. He actually just told me that he's working part-time for like a deep tech startup. So also great to chat about this more perhaps during the networking session. He has like background in industrial engineering and is really interested, of course, in industry tech and climate tech in general. So really great to have this chat today about in this industrial heat tech, how I call it. And funny fact also, he loves to learn. So he once took a 2-week hunting holiday in the sense of just to get his hunting permit. So if any hunter is out there, also connect with Nick. Handing over to you, Nick.
Awesome. Thanks for the introduction. So happy to be here today. And as Lena said, I'm looking back on 3 great months at First Momentum. Was a really great time during my summer internship for my MBA. And we decided to make this session for me to kind of share my deep dive into industrial heat during that time. We've looked at a lot of startups in that space, and that gave me also the opportunity to kind of dig deeper into the space. And now happy to present and kind of share what I've learned over the time with you guys. So thanks for tuning in, even during the precious lunch spot. And let's get going. So what I want to talk to you guys about today in the industrial heat segment is kind of first an explainer. What is it? A bit looking at the market, but also kind of clustering different solutions out there. Then going into the topic, why is it hot or why is it hot now? then leading over to a bit of the technical side. Really just wanted to pick two technologies that I think are really interesting right now, heat pumps and resistive heating. And yeah, then looking a bit into current challenges of the ecosystem and closing it out with some cool example startups that are really making a wave and really changing the space right now. So yeah, feel free to ask some questions, and I'm happy to get into them um, in the end. I see that you can see the screen, if that's correct. Oh, somebody can see the screen,
I
so I'm
think
not
it's just
really sure.
yeah, some people. I will check into this. You can
Um,
continue, Nick.
let me just reshare, maybe that helps, and then we just get going, and I hope it solves it for everybody. All right, Lena, can you see it?
Yep, and I think
Yeah,
also
okay,
others. So
perfect. Then let's jump into it. So, what is industrial heat? It's thermal energy in the form of heat, very physically speaking, and it's used in all industrial processes. And it's really interesting from a climate or a global warming perspective because in 2016, you can see here in the chart, uh, around 20% of the global CO2 emissions are actually coming from industrial process heat. So it's a huge industry and by that also a huge problem. And yeah, the interesting part about it is there's really no thing that can replace process heat. It's really needed in the industry, and it includes things like melting, curing, drying, cooking, but also many more processes. So I'll go into a few of them. But pretty much every major industry really needs industrial heat or process heat. And so there's really no way around it. It's just the question of how do we get it and where do we get it from. So one key metric of industrial heat is the temperature in the process. And I wanted to show you this diagram here to kind of show you a little bit of what temperature ranges we're actually looking at. So in the diagram here here in the left, you can see on the x-axis the temperature that we're looking at, and then there's not really a y-axis, but just stacked the kind of different applications. So you see, looking at like, for example, textiles or paper or food, you're in the lower ranges, like somewhere from 50 to maybe 200 degrees Celsius. Then when you go to chemicals and heat treating, you kind of already go up to a higher range, also kind of crossing the 500 degrees for the first time. And then where it gets like really hot is any non-ferrous metals, stone, brick, cement is really crossing the 1,500 for the first time. And then kind of the champion of temperatures, so to say, is iron and steel, and that reaches the yeah, all the way up here, close to 2,000. And so now looking at the kind of the temperature from a different perspective, here on the energy consumption, and you can see that there's pretty much two big peaks. So here on the left, in that 100 and 200 degrees Celsius space, you can see that there's a lot of energy consumption happening, and this plot is now Germany as an example. And then you can see the 1,500 degrees for iron and steel that are also like a huge spike. So that's kind of the main needs of temperature, so to say. But then you can also see that there's a quite a big of chunk somewhere in the middle. That's yeah, that is, for example, here the blue is finishing, then chemicals has a big share here, and then iron and steel also here is in the bit lower temperatures for like preparation steps, and then the final big chunk for iron and steel is here on the 1,500 range. And yeah, kind of a similar look at it just from a emissions perspective. So this is also just in Germany. Here, Treibhausgasemissionen, so any CO2 equivalent emissions, and you can really see here the heavy hitters on the bottom. Here it is iron and steel. Then you have chemicals, you have cement, but also here paper, for example, or food are making a big dent into it. So these are kind of the industries that need the most addressing to get rid of all the CO2 equivalent. So that much about kind of the demand and also looking a bit into the temperatures. To understand industrial heat a bit better, it's also interesting to look at thermal load. That's like one of the other key characteristics of industrial heat. It basically means how much heat is being generated. So first you have temperature, and then you have the amount. And to give you an example, for like a light bulb, for example, you notice by just touching it, it gets hot, but still the thermal load of it is actually really small. So you would never think about using a light bulb, for example, to heat up the room, because the temperature would be enough, but the thermal load would just not be enough. So that maybe as a small example. And you can imagine, I think, that if you want to melt a large amount of steel or iron, that there's a really high thermal load needed. Now moving up a little bit away from just the temperature and the heat itself, going into the money. So looking at the market size, current estimates are around 41 billion, going into 62 billion in 2030. But I want to highlight here that these estimates are looking at like boilers, furnaces, and heat pumps. But I'll show you in a second that the space is actually quite a bit bigger. So they're mainly looking at like the conventional or appliances that are being used, but there's way more coming. So I think there's more growth in that market to be seen if you kind of expand the scope of these studies a little bit in the future. And yeah, so I think the zero carbon industrial heat sources can be clustered into 4 categories. And you'll see that there's actually one of those categories is mainly what these market studies are looking at, but it goes wider than that. So the first one is zero carbon fuels. I think you've all also heard about that. It's fuels that have a net zero carbon impact. So it doesn't mean that they're being burned completely clean, but whatever the emissions are that come out of the burning of the fuel, that's actually been taken out of the atmosphere while creating the fuel. So as a net, looking at the whole process, you get to a net zero. And there are a couple of different ones in there, like synthetic fuels, biofuels, hydrogen, and for example, synthetic ammonia. I think you've probably heard of the most of those. But yeah, the good thing about them is they can replace the current fossil fuels pretty easily because they're very similar. So some can actually be replaced just one on one. And also looking at kind of the thinking about infrastructure, the logistics behind it, it's all very similar. So there's an ease of implementation when looking at these fuels that is really useful currently in the transition. However, looking at some of the challenges, the zero carbon fuels struggle to be cost competitive. It's quite expensive to create them. Then I talked about infrastructure and transportation, and while it is kind of easy to use a similar infrastructure as today, looking at scaling, there are coming other problems into it. For example, if you would go all in on hydrogen, you would be creating hydrogen somewhere, probably in the global south, where you have more um, more heat, more sun available, and then there would be a significant issue in always shipping or transporting that hydrogen to, for example, Europe or other countries. So there comes complexity into the system when scaling that. Um, and when you think about industrial processes, some of these fuels can be reactants in the process. So you would have a problem when using the fuels in your processes, because they kind of can destroy the reactions that are going on. And yeah, then let's look into zero carbon heat. So this is heat that's directly coming um, out of renewable energy sources. So, for example, solar, thermal, or nuclear, and just using these sources to create energy straight out of that. Um, I think a positive, as with all other renewable sources, the marginal cost of operation is very cheap. Once you have the solar panels put up, the sun is for free, right? So the marginal cost of more electricity or more heat is super low. Um, but also these kind of come with their own challenges that we need to still solve. Um, Solar, there's low areal density, so if you collect heat through solar, you need a huge amount of space. You have geographical limitations. The sun needs to shine, so you can only operate it during the day when the sun is actually up, and you can also only operate it in areas of the world where there's actually enough sun and also consistent sun and not often covered by clouds. Then thermal, currently only low temperatures are achievable, at least with manageable digging effort. It just limited by the temperature that exists in kind of the soil or the earth. Um, and also here you have geographical limitations of how the ground is made up, and is there actually any thermal heat available that you can dig for. And then nuclear, I think, especially in Germany, well or often discussed topics. Clear challenges are kind of the safety, the waste of the material, and then also regulatory compliance that can pose significant issues. Then number three, the electrification of heat. Um, in my mind, the most promising solution. It can generate high quality heat and also reach very high temperatures, up to 2000 degrees. Still under development, but hopeful. And there are a couple of different methods that how you can actually generate heat out of electricity. Um, Also well known currently out of the German press are the heat pumps. Then there's induction heating, there's resistance heating, and also heating through light. And now talking a bit about the quality of electrified heat, there's a unit to measure it. It's called COP, or COP, for coefficient of performance, and it basically measures the amount of heat you generate for the electricity you put into the system. And most of the solutions are being limited to COP1, and then you even need to deduct efficiency from that, just because, for example, if you burn some material, you're not going to get more heat energy out of that material than the chemical energy that is being stored in that material, and that means a COP of 1 at maximum. However, heat pumps are actually they can actually achieve a COP of higher than 1, because in the end they're transferring heat and not generating heat. But I'll get into that later in the section, kind of how it works. But the COP is something to kind of keep in mind when looking at different technologies, and having a higher COP is more desirable. And here we've observed startups that aim for temperatures up to 2000 degrees Celsius with resistance heating, and also we've seen the first industrial grade heat pumps that are trying to reach at least 550 degrees Celsius, so quite a bit higher than anything out there currently. Looking at challenges for electrification of heat, the high temperatures, since you're not burning things, it doesn't come natural to have high temperatures. You can only reach zero carbon when there is actually green electricity being used, and that needs to be either coming from the grid or from some other green electricity source that is close to your plant. Then there's still significant cost involved. For example, heat pumps are really expensive. And then already touched upon it is the limitations of the electrical grid, not just if the electricity is green, but also the capacity of the grid. How much energy are you actually allowed to get out of the system to run your facility? And then the last one, not really generating heat in that segment, but improved heat management. So looking at the loss during industrial processes, there is quite a lot of heat wasted. And here you can kind of see the split of the temperatures where the energy is, or the heat is lost. And you can see that about a third is below 200, but then around 40% are actually above 500 degrees. And you can imagine the amount of energy still stored in that temperature, or in that hot medium. So there's really significant improvement to be made to not waste such high value heat. Couple of methods how it can be done is, for example, I think an obvious one, better insulation, really taking care of not wasting the heat. There can be better processes, for example, processes that kind of recycle the heat and do the first warming up of materials with excess process gas that comes out of a process, so it can kind of be recycled and still be used for at least the lower temperatures. And then a really big topic currently is the topic of heat storage. Just using excess heat somewhere to put it into storage so you can take it out again a little later. And I go into a few startups that actually are looking at that currently. Challenges with that, I think mostly the cost, and then it needs a change in the processes in many cases. So for example, existing plants, it's not always easy to just completely remodel them to change the process to store or to not waste the excess heat. All right, that was kind of the wide overview over the industry from a perspective of why is it, or where is heat needed, why is it needed, and also then what kind of technologies and ways of creating heat are out there. And now looking at the next chapter, why is it hot now? I think there's the very obvious one. There's climate change, and since there is 20% of global emissions coming from industrial heat, I think it's super obvious that this is a huge lever in creating change. But then also on top of that, I think there are some geopolitical and societal trends that actually give it some more tailwind just now. Ukraine war being one of them. The gas prices have spiked to unprecedented heights. Everybody thought gas was kind of the way to go for the midterm, long-term future. And now it suddenly doesn't look as good anymore, and also not as dependable anymore. I think there's an increased awareness currently, and that is also the public really putting pressure on companies to become carbon neutral. And also, I think the carbon neutrality is being used for employer branding and kind of attracting talent. And then the last one, the political landscape. Significant subsidies and grants are out there for these kind of solutions. There's regulation that you need to reduce your emissions, and then the whole topic of carbon credits, carbon tax, that's also kind of always looming over companies, makes it more attractive to change. Now looking a bit more into the technical side, and I mentioned before, I really want to focus on two technologies. First of them is heat pumps, and then the topic of resistive heating. Heat pumps, here I found a really good quote. There are no silver bullets in the fight against emissions, but the closest thing we have is a heat pump. And that really comes back to the COP that I talked about earlier, this coefficient of performance, where heat pumps can reach 2 to 4, whereas the other known heat sources can actually only reach 1 at maximum. And because of that, heat pumps should really be used wherever they can, just because it saves so much energy compared to other forms. And yeah, it talked a little bit about where this COP is coming from, but yeah, diving a bit deeper into that, the heat is actually not generated by heat pumps, it's just transferred. So the heat is transferred from a heat source into that process, and it's very similar how a refrigerator is kind of colder on the inside than on the outside. It transfers heat from the inside to the outside, and I mean that process costs uses electricity, so it uses energy, and there is also some excess heat in the form of a refrigerator. You wouldn't want that in form of industrial heat. You actually don't mind it, but in your home with a refrigerator, you would notice that because there's kind of warm air coming out of the back of the refrigerator. And this is kind of the system that you also have in place with heat pumps. So it uses this heat source to draw from and puts that heat into the process where you want to have it. But since it's not generating heat, it comes with limitations. So the difference of the temperature is high. It becomes more challenging to transfer the heat. And additionally, with higher temperatures, there's more energy needed to transfer the heat. So the process becomes less efficient. Now looking a bit into the kind of the technical specs of it. So there is, or the core component of a heat pump is this refrigeration cycle, where the refrigerant, usually a liquid or a gas, is being moved through the cycle by a compressor, and it kind of moves around this circle where here in the evaporation stage, so it's actually a liquid before and then it becomes a gas, and that is happening by getting heat or energy from one of the heat sources, then moves into the compression, um, and then goes through the condensation pressure process, so it becomes a liquid again here. In that process, there is temperature being or energy taken out of it, and then the refrigerant kind of continues here and goes through expansion. That was not super in-depth physical description, but I hope you kind of understood at least the main kind of working principle of it. Then also heat pumps have current challenges, even though it's called the silver bullet. The cost of production is still really high, and right now heat pumps that generate a higher temperature often use several refrigerant cycles kind of stacked next to each other, and you can imagine that increases the price. Then the challenge of increasing the temperature range. So heat pumps are currently being used up to about 200 degrees Celsius. So you can see that when you look back or think back to the diagram on top, there was actually a significant peak in that temperature range. So it does work for a good amount of applications already, but extending that temperature range would obviously increase or make more applications possible. So there are startups out there aiming for 550 degrees Celsius, and I'm super curious to see if they actually manage that, but that would be really awesome. Then another one is the refrigerant material. Currently, it's often toxic and flammable. So even though it's a sealed and closed loop, obviously that's not ideal. So they're trying to move away from these materials to safer and also cheaper options. And there are first solutions coming already with for example, water or just well, gas is not really a good description here, but I think even with just normal air coming out. And then the compressor technology, the compressor is really what moves the refrigerant through the cycle. So it's a core component, and it needs more research to also unlock what I just talked about, the other refrigerant materials. Then moving on to the next one, resistance heating, also called ceramic heating because of the materials used. So as the name suggests, it's used by the physical principle of electrical resistance, and also similar kind of to the light bulb. So the wire gets hot because you put electricity through that. And similar here, you use a ceramic where you put a high voltage on both ends, and due to the resistance of the ceramic, there is a large amount of heat being generated. And the way it's being used in the industrial process is that the ceramic is placed into a stream of process gas, could be air, and then that gas is being heated up, and you channel kind of that gas towards the heating application, for example, a furnace, where then the actual process where the heat is needed takes place. But a bit of a reminder, since the process gas temperature depends on the ceramic, because the ceramic needs to give off that temperature, the ceramic will always be higher. The temperature of the ceramic will always be higher than the temperature of the gas. And when you think about wanting to reach, I don't know, for example, 1,500 degrees Celsius for the process that you're looking at, then the ceramic needs to be more like hotter than that, higher temperature than that. For example, 1600, 1700 degrees. Here, looking at a few advantages, super high temperatures are possible. It's a clean source of heat, so there's no exhaust or emission from any combustion, so not even locally. So it's not net zero in the way a zero carbon fuel would be, but there are actually no local emissions. And there's a safety aspect to it. There's nothing burning. I mean, it's still high temperatures, don't get me wrong. You still wouldn't want to be in near that process gas, but there's little danger of fire or explosion. And current challenges with that technology around reaching high enough temperatures to replace the conventional heating sources. I think especially being able to unlock the steel industry would be a huge game changer. And then material choice is really difficult for a number of reasons. For example, you need heat resistance for all these high temperatures, but also there's oxidation happening from the heated process gas, which deteriorates the ceramic. And then also when you're looking at the material, you need to keep in mind the conductivity or the resistance of the ceramic, which enables the process in the first place. And then I think you've seen this a couple of times now, but price competitiveness or cost is still an issue with these kind of technologies. Now, kind of summing it up, I mean, now we looked at some challenges on some deeper levels, but kind of looking at the whole ecosystem and where the challenges lie with the ecosystem. I think high temperatures, I've gone over it a few times now, so don't really want gonna go deeper into it, but higher temperature is always better because you can have more applications. Then the electric grid is or will become very important. Most of the solutions out there are based on electricity to be independent of time, weather, location. The electric grid needs to be the transporter of that energy. And there's an article out there stating that kind of calculates the amount of electric grid or the amount of energy going through the electric grid, and they come up with this number where the wires stretched out for the grid needed would actually be long enough to reach the sun. And just thinking about that, I think is pretty crazy. So that will be a huge infrastructure challenge coming up. Then new materials, especially in high temperature applications, for example, new ceramics, but also new refrigerants for the heat pumps. I think there is still a lot of research needed to look into that and really make it process ready for the everyday industrial use. And that will just take testing and development time. Talked about it a few times now, cost competitiveness. And there's an aspect of just research and development that drives the cost. But the industrial world is driven by cost, and in the end, the products need to be cheap and cost competitive. So even though a plant would want to change their process, they are kind of limited by the economics of it. So yeah, for really a wide scale adoption, these technologies still need to decrease in price. And the last one is the integration into current processes. These industrial plants are designed to run for decades. So plants will not just be popping up again everywhere, but there's an amount of retrofitting needed. And so the new solutions that are coming up, they need to be able to be plugged into the existing processes. Otherwise, I don't see a wide adoption of it, at least not in the near future. All right, then looking at a few startups, also always super exciting, I think. Um, I just go through them a little bit. I have the name, and I'm showing a picture, and then I'll give you a bit of a voiceover here of what they're doing. So the first two, Heliogen and Odga, I hope I'm pronouncing that right. I don't know actually. Um, they somewhat do a similar thing where they collect. Here they have these solar panels. Actually, they're mirrors, but they redirect the sun into this tower, and you can kind of see what the tower is doing in here, where they shine the light through this hole, and they generate heat by, or they can use the heat from the sun by sending like a cool um, process medium in there, and then it gets heated up from the light, and the heat gets transported off through this uh, tower to the bottom, and then it can be used. Um, then there are a couple ones into thermal storage. So here, this one is Rondo. You can see it's based on these cement blocks. Um, there is Antora, and this one is actually very similar to Energy Nest. This one, I think you might have heard. I think they're quite big by now, and they have these tubes that you can see on the right that they put in these blocks, and they run warm gas through it to save the energy in the system, and then to take it out, they send cold air through it, and then the air again gets heated up, and they can take the energy and the heat out of the system. Then there's Kraftblock. They have really slick outside design, but you can really see what's happening from a technical perspective. So they do very similar things as the other ones, so I didn't include a picture here. Then there is Coolbrock. They do electric heat through the spinning of a rotor. So this is kind of the outside look on the left, and on the right side you can see a cut open machine, and you can see the spinning of the rotor. And by that spinning, it's a bit like a turbine, so they can generate heat with that. And then there are a couple ones focusing on heat pumps. So there's Heaton, for example. They use waste heat as a heat source, and they can reach up to 200 degrees with their solution. Then there's Futura Heat. They also use waste heat. They're aiming for something around 150 degrees. And then this one, Earthium, is something I mentioned earlier a couple times because they're the ones that I saw at least that are aiming for 550 degrees, so significantly higher temperatures than the other ones. All right, that is kind of the rundown. I put some sources on the bottom. I think you will get access to this page later, where you can also go through the sources. Some really cool articles in there. So feel free to check those out. And yeah, thanks so much for taking the time, and I'm happy to answer any questions that you have.
Okay, this is a sound effect I needed to use. So now
Sounds very real.
it seems it doesn't automatically stop. Yeah, I hope you really felt like honored, Nick. Thank you so much, yeah, for this really insightful session. I'm pretty sure there are some questions. So yeah, I would actually like encourage everyone also, as I had said before, use also the live call-in if you want, and we just get you basically also on the floor. Yeah, just wait until we accept. But already, yeah, first question actually from Simran. Thank you for the insights. Are there any early indicators or available data that suggest adoption and integration of heat pumps in the industrial sector in Germany already?
Yeah, so I don't have any exact numbers, but this is already going on. I think for many reasons, the industry is already trying to change, and I've seen a lot of articles around this stating that there is already adoption happening.
Yeah, actually, one question I also noted was like how in general, how open to like also partnering with startups and innovation in general do you see these industries that like are mainly affected or need basically the innovation?
I think it's kind of on a need basis, but since the need is strong and conventional players are currently not, at least not all of them doing it, I think there is also collaboration going on. I don't have a detailed inside view in the industry there. Um, but for example, for heat pumps, there is also many bigger players. For example, ABB is providing heat pumps. So kind of also referring to the question before that, that's there is already industry adoption on these. Um, but I think, yeah, with startups also supported by grants, for example, where it's fairly cheap right now to test these solutions in a pilot. Um, Based on a grant, there is collaboration or there's openness for collaboration.
Okay, cool. Yeah, I really hope that one person tonight or today will uh, call in just that we can try. So really, even if you just have a comment and no question, please call in. I would love to try this one. Um, but yeah, I mean, perhaps also a question that I think can be helpful to start. Like, how do you? Because I mean, I know you looked at a couple of like startups also for basically first momentum in the deal flow that were covering that topic. Was there? How did you evaluate these startups? Was there something, especially from, I mean, a technical side that you had mentioned, for example, the COP, or any detail that would make it different? How you would look at these startups than at others?
Yeah, I mean, I think it's similar to all the deep tech startups that we looked at. I mean, the team was super important. There were a lot of, yeah, or there's a lot of research going on at universities in this space. Um, and yeah, so we looked at the tech that was coming out of it, but also the team behind that. Um, and I think we looked a lot around the temperature. So is this something that can kind of unlock these new temperature ranges where you would have a competitive advantage with the tech? I think this one was a big one. And then after a while, I think we gotten a pretty good sense of the industry and kind of the technical challenges with these solutions. And yeah, I think it went a bit into a direction where just the smartest or the most well thought out solution would be the most appealing to us in a sense. And since it's quite a dynamic field right now, it was also nice to kind of be able to compare a couple of startups and their solutions and hear their thoughts on different technological approaches.
Okay, cool. Makes totally sense. Uh, Yeah, another question from Andreas. How do you think a successful startup will look like in this space? Just owning the IP and working with partners, or actually becoming an OEM?
Um, I mean, I think it can go both ways, to be honest. I I think that um, the first steps need to be done kind of in-house, so to say, and they need to operate as an OEM in the beginning at least, just to make sure that the technology works, to have kind of the grip on the development, um, and then at later stage, I could see both ways. I think it also comes a bit down to funding, and it's probably also a regional preference. From what I've heard from also some startups, think the US VCs would say become an OEM and own the whole thing. And I think in Europe there's a bit of a notion towards um, rather license it and own the IP, work with partners, so you reduce the complexity and also the need for funding. But I think both ways can work long term. I think short term, there's no way around owning the whole thing and gaining the trust with the partners, making sure the integration in their system really works. But then later I could see both ways working.
Cool. Any other questions? If not, oh, there comes one. Yeah, Simran. Is there already a startup like that in the First Momentum portfolio? Unfortunately, not yet. But we definitely are looking into it, as Nick has proven. But yeah, we will definitely also let you know whenever we have made that investment. Also, yeah, no worries if you have to run. I know we also ran a little bit late today. But Nick, thank you so much really for this super insightful session. We will switch over to Zoom for, yeah, that's actually true. Max turn to, yeah. Look at Turn, one of our companies. I will share actually the link, then you can also check that more now in the chat. Yeah, we basically switch over to Zoom for the breakout session. So whoever wants to meet another scout or someone from the First Momentum team and has 10 more minutes, switch over. And yeah, will be lovely to see you there. Nick and me will be waiting for you over there. Thank you so much for today's session. Here comes the link to Zoom. And then, yeah, see you also, hopefully all for the next time, for the next session.
Yeah, thanks so much for listening, and yeah, see you soon.
Bye bye.